Precalc Chapter 6, Section 3, Part B notes. So this is kind of where we left off, is looking at vectors, component form, linear combination form, and now we're looking at the direction of the vector, direction angle. And so if you have your vector u right here, you can see our vector from initial to terminal, and then we have some theta, our angle measure, our direction angle. So we have u as the unit vector, so we know that u has a length of 1 for this example. We can actually go back to our right triangle trig here, and we have some change in x value, we have some change in y value to create our unit vector, and it creates this right triangle. So then we know that vector u could be made in component form as the change in x comma change in y. And then we can also write that because we know that from the unit circle that this point here xy is really the same thing as cosine theta sine theta. And we can do this because it's the unit vector, so it's like the unit circle. And then this is going to also be the same thing as cosine theta I plus sine theta j if you want it in the linear combination form. So those will be the same. To find theta, if we don't know theta, we can find it by using the tangent. The tangent of theta is just going to be the opposite y over the adjacent x. And so we can do the inverse tangent of both sides to find the theta value. So for any vector v, so if our magnitude is not 1, our length is not 1, we can actually pull out that magnitude v and then times it by our actual cosine theta sine theta. And so you're basically pulling out the scalar. So cosine sine are still the direction, and then you're pulling away the magnitude. And that's the same thing if we wrote it as the magnitude v cosine theta I, if we're going to put it in linear combination, plus the magnitude v sine theta j, and those are the two forms. To find theta, we're still using our tangent, so inverse tangent of y over x, or you could say the inverse tangent of sine theta over cosine theta. So example, find the direction angle. So given this vector, and this is a linear combination, so this is to be the same thing as the -7 comma -4 if you prefer the component form, but it doesn't matter. And so realizing that this is a change in x, change in y, to find theta, all we have to do is do the inverse tangent of -4 over -7. And you plug that in, you find that our theta value is approximate to 29.75, but there's an issue with this degree. If we look, we really have to think about the problems and where we're at. -7, -4 from standard position, so -7, -4 would be down here like this. If we apply our theta value of 29.75 is only up here, and so that's not right. We need this angle, and so we actually have to do the 180 plus the 29, so we have to add 180 degrees to find the actual theta for this vector. So this vector's theta value ends up being 209.75 degrees. And so you're really careful here, because you can do the math right, but if you don't understand really what's happening in the problem, you won't get the correct answer. Okay, one good application problem, and the project I have for you uses the same kind of knowledge. So a plane at 724 kilometers per hour at north 30 degrees east, and we have a wind at 32 kilometers per hour from the west, which means it's going east. So find the resultant direction and speed of the plane. So when you have applications, the speed is like the magnitude. And so if I draw this, first thing to figure out that we are going northeast, so north then east, 30 degrees. So we have this 30-degree angle right here. The plane is flying in this direction, and it has a magnitude of 724 kilometers per hour is the magnitude. So let's call this vector u. Then we have wind, and wind is always blowing, for this problem, is blowing from the west, so it's going east. I'm going to put it at the end of my vector showing how it goes west. So this is going to be W, and the magnitude is 32 kilometers per hour. So the resultant, what ends up happening? Well, the wind ends up pushing the plane to the right a bit in this motion. It will actually help it out a little bit too, because it's kind of from behind, so it was push the plane, so it should speed the plane up. If we think about our vector notation, this is actually U plus W would equal the final vector, we'll call it V. And so we have to go through our math. So let's first take and write the two vectors. So vector U is going to be made of our 724 is our magnitude, and it's going to be multiplied by the cosine of our angle. Now, our angle is not 30. It's the angle in standard position. So standard position up there would be 60. So cosine 60, sine 60. So from what we just talked about, we're pulling away the magnitude, and then the component form here is really the direction. So we can multiply through our scalar. So doing 724 cosine 60, comma 724 sine 60 is how you can write the actual component form for vector U. So if we use our right triangle trig, this would be 362, and it's 724 cosine 60 is 1/2, and then 724 times square root of 3 over 2, so it's going to be 362 root 3. So I'm keeping that exact, but there's my component form for vector U. If we look at W, the wind, it has 32 as the magnitude, and the component form is cosine 0, sine 0, because it's going to the right at a 0 degree angle. So this would be 32 times cosine 0, 1, so it would be 32 comma 0, because sine of 0 is 0. So there's the component form. And so to find vector V, we're going to take vector U, 362 comma 362 root 3, and then add to it 32, 0. And so the result we end up getting for vector V is 394, 362 root 3 is the component form. So that's the math, but now we got to apply it back to the problem. So we have to first find the magnitude of V, which is going to be at the speed. So it's going to be the square root of 394 squared plus 362 root 3 squared. I'm keeping my values exact, so it's my final answer will be approximate, but it's precise. So it's 740.52 kilometers per hour. So you can see how its speed has increased with a tailwind. And then we want to find theta. And so to find theta, we do the inverse tangent of 362 root 3 over 394. And that's approximately 57.85 degrees. But again, that's the standard position. That's like this position is that angle. But I want the other position to give the coordinates or the bearings how air flight gives it. So it's got to be northeast so much. So this corresponds to north 32.15 degrees east. So then that would be the answer, is that the actual resultant direction and speed would be 740.52 kilometers per hour at a north 32.15 degrees east. So that would be the result for that plane. So that would be the end of 6.3, and we'll be done for the night.